Hey, how you doing? Seb here with a new intro and in a new room, otherwise known as my shed, or even the lab if we really want to get fancy. So while we're in here, let's go on a quick tour and see where all the magic happens. So over in this corner I've got a little collection of all my electronics books and all my circuit schematics, an original filter that turned to shit when I was trying to make the breadboard computer, a box of Grandpa's old knobs. In this little pile we've got some old Dick Smith books that I originally grew up with, where you can make the beer-powered radio. Only in Australia would you be able to find something like this. Maybe one day I'll do another little video in response to Sam's Everyday Electronics Magazine's videos, and take a bit of a look at how ridiculous some of the circuits are in this old book. Some Forrest Mims ones, a couple of J-Car books. So this whole little area is basically my little soldering station, where I'm putting together all the circuit boards and modules. I have the whiteboard with all the modules that I'm planning to make. The crazy clock, the sequencer, dual filter, sample and hold. There's a lot of stuff that I want to get through. Up on the wall we've also just got a bunch of little diagrams and pinouts for transistors. We have my little resistor cheat sheet, and all my cap codes, the multimeter, little paper roll holder for all my wire and solder, this little weird creepy thing, all my little tools, soldering iron, and then down the bottom I've got all my little drawers for all my resistors, capacitors, LEDs, all my chips and diodes. And then another one over here which I haven't filled yet. We've got some jacks, big tray full of pot, some switches, cables, MISC, a lot of stuff really. I've also got my lucky dip tray, just all the random and spare components that I pull out of breadboards once I'm finally done with them. But it's an absolute mess in here, so it's both my favourite and most hated drawer. If you want to find a 100k resistor, good luck. Some spiderweb covered old speakers, and then the old pedestal drill that Dad gave to me, which has been perfect for drilling all the panels that I need. A few pairs of safety glasses and just random tools and fly spraying crap down here. So down here, first got the aluminium that I'd used to make all the panels. But that's not what I want to show you. What I've got in this box is all the old kits that I used to make when I was a kid. So this is everything that I used to practice to solder. It's like a timer. I think that's a buzzer or something. What's this? The voice operated relay. So there's a lot of stuff in here that I'd like to be able to go through with you all one day. Just a lot of random things, like a little, I think that's a keyboard project or a little stylophone. I think that was something I made for school a couple of years ago. But yeah, it's just my big box of random crap basically. In the middle of the shed, I have my old table that I've had since I was about 11. But on here, we're gonna take a look at all the breadboarding for all the modules that I plan to make. And of course, we've got the obligatory plastic plant, and then all my lights and whatnot, and the wood heater in the corner. So we've finally moved on to a new episode, and today we're going to focus on what I'm calling the crazy clock. As you saw in episode 1.5, we use the clock to keep every module in a patch in synchronization with one another, because without it, everything is just a mess flapping about in the breeze. But why the crazy clock? Well, I'm going to be having 3 individual clock modules all behind the same panel, each one able to be fine-tuned from fairly slow to really fast. Each of them also with selectable auto or manual modes. And then on top of this, I'm also going to create an inversion of each clock, so we get the not clock. Each of these clock and not clock signals will eventually be taken to a logic module, so we can create a bit of a dynamic rhythm with a final clock signal. So rather than having a straight 1, 2, 3, 4, 1, 2, 3, 4, we can have 1, 2, 3, 4, 1, 2, 3, 4. Something like that, basically. But that's getting pretty far ahead in the future. Today we're just going to take a look at the process of turning the clock breadboard into a final module. So let's move down to my breadboard zone and go through a quick recap of how the Ben-Eater clock circuit works. I've also got to make a few repairs to it, so let's do some building and learning along the way. So as I've spoken about before, this clock module was originally part of the Ben Eater 8-bit breadboard computer, which I did actually have a bit of a crack at making, but the problem was it got to the point where I had to order the RAM chips from the USA, and it was quite expensive, so it just wasn't worth doing anymore basically. But I got it to the point where I was able to add one number from the A register to another number in the B register, and then get a result in the arithmetic and logic unit. But beyond that, it doesn't really do anything beyond counting. So at the moment, I basically pulled out a couple of wires on this thing that I shouldn't have, and I can't remember how it was actually meant to be wired. So what we're going to take a look at is just a bit of a rough idea of how the whole module actually works. So what I do know is that there were a couple of outputs on each of the 555 timers. So what I'm going to quickly do is stick an LED into each of these, just so we can have a representation of what's happening on each of them. To keep it consistent, I'm going to get rid of this red LED and make it a blue one as well. Alright, so fingers crossed, if I put in the battery, we should see this one start blinking. Very good. Now I have to find my screwdriver so I can show you how we can adjust the speed. So what we basically have is just a little 1 amp potentiometer and then a 1 UF timing capacitor. So combined with this whole circuit, we have a free running oscillator, which you can see goes fairly slow and then ridiculously fast, to the point that it actually just glows because we can't see how fast it's actually flashing anymore. Let's just take that right down so it's not too annoying. Now, as I mentioned in episode 1.5, you can find all the information about this clock module with Ben's videos just up here. He goes into far more detail about how the 555 timers work in each of their modes, more than what I could deliver. And since it's already covered, there's no point rehashing the same thing all over again. What we should also see is that with this 555 timer, if I press the button, if I hold it down, we now see that the LED turns on, and if I release the button, it turns off. So this is how we can have a manual clock pulse rather than just a free running oscillator. And then over on this 555 timer is where we can use our little selector switch to select whether we want the LED on or off. So if I flick it down, it should hopefully turn on. Hey, there we go. The connections are a little bit dodgy on here, so I never quite know if anything's going to work properly or not. So if I flick it off, as you can see, it's a bit skew if. Come on, there we go. So we basically have a little selector switch now. So as you can see, we have 3 different modes. We have the free running oscillator, where we can control its rate or frequency, then the manual clock pulse, and then our little selector pulse. Or selector signal, I should say. Now, to get a bit of a better idea on how this circuit works, I'm going to quickly pull out the schematic. So we don't need this for the time being. So as you can see, we have the 3 different 555 timer circuits in their different modes. Up here we've got the free running oscillator, and then in the middle here, we've got the manual clock pulse. And then over here is our selector signal. So if you just ignore this bottom part for the time being, you can see that we've got 3 different 555 timer circuits. But what we basically want to be able to do is use the selector signal to choose whether we want to use the manual clock or the free running oscillator. Which brings me down to the part down here. Now, it wasn't until I studied a computer science course that I realized that this little circuit is what is known as a multiplexer. So what we can basically do with a multiplexer is take many different input signals to one common output with the use of a selection signal. So you can see with this little arrangement, we're able to use the selector signal to choose whether we want the manual clock or the free running oscillator. And then along here, you can see there's a little, what is called the halt line in Ben's computer, which basically goes through an inverter and then up into an AND gate. But this is basically just used to stop the clock so that it doesn't produce any signal on the output whatsoever. But from the AND gate is the final output, which you can see is called the clock. And this also comes up to another inverter called the NOT clock. Now when I originally built the clock circuit, I was building this whole arrangement, and as you can see, it uses 1, 2, 3 different chips. And I was like, well, that's kind of quite a lot of chips for a very simple function. Is there a chip out there that can replace all of this? Well, it turns out that yes, there was. I was able to go down to JCar and pick up a chip called the 4053, which basically takes two input signals to a common output, and then we can use a selection signal to choose which one of those inputs we want to take to the output. So this is a data sheet for 3 different chips, just all in the same document. But I'm just focusing on the 4053. But we can see in this little paragraph down here, the CD 4053B is a triple 2-channel multiplexer having 3 separate digital control inputs, A, B and C, and an inhibit input. Each control input selects one of a pair of channels, which are connected in a single pole double throw configuration. Now this chip has way more features than what I actually need, but what I'm trying to do is just control the free running oscillator and the manual clock. So it's nothing too complicated. So moving to another page. So taking a look at this functional block diagram, it's a pretty complicated thing that's going on here. And it's probably not really intuitive to be able to explain all of this. I mean, I'm struggling a little bit myself to be able to work it out. So what I'm going to do instead is just draw the block diagram of a 2-to-1 multiplexer, which will make a lot more sense rather than just all this nonsense. So if I draw a couple of black boxes, so our free running oscillator, our manual clock, and our select signal. So the symbol that I'm drawing now is just the block representation of a multiplexer. So as you can see, we've got 1 input, 2 input, and then both of these can then come down to a common output. So if we imagine that internally inside the multiplexer, we have a little switch that can select between one of these 2 inputs. And then at the top, we have what is known as the select line. So if we imagine that this select line is connected to ground, then that produces a binary 0 on the input. And let's just say that the switch then flicks to the first input. So now whatever is coming through here can now travel through to the output. Then if we connect the select signal to a positive voltage and produce a binary 1 on the input, then the switch will suddenly flick down to the second input, and whatever's now on this line can travel through to the output. So we can take the free running oscillator into one of our inputs, the manual clock pulse into the other input, and then our select signal comes into our select line for the multiplexer. So now we're able to use the 555 timer for the select signal to use the selection line on the multiplexer, allowing us to switch between the manual clock pulse or the free running oscillator. Now let's also just imagine that we have another line on the multiplexer called the inhibit, and this basically just stops the multiplexer from working altogether, so that even if either of the signals are coming through the inputs, it doesn't matter what the select line is doing, nothing's coming through the output whatsoever. So the multiplexer is just effectively turned off. Now I have to take a look at the datasheet again for the 4053 to work out if it's a 0 or 1 that uses the inhibit line to be able to stop the chip. But for the most part we can just assume that there's an input signal that controls this. So while we have a drawing here, let's just keep going and I'll give you a bit of an overview of what my plan is for the clock, or at least just one of the clock modules that I'm planning to use. So if this is now our final clock output, we'll then have this come down to an LED and through current limiting resistor to ground. We'll also take this through an inverter and do the same thing. So now we can have the clock signal and the not clock signal. So if this one's on, this one's off. And if this is off, this is on. So they're just going to keep doing the opposite from one another. In the case of the 4053 chip, we have 3 of these 2-to-1 multiplexers that we can use. So my plan is to repeat the free running oscillator, the manual clock pulse, and the select signal 3 times. So then we can have 3 different clock signals that we can choose from to drive other modules in the system. So now that we have a bit of an idea of how the multiplexer works, let's move forward with actually connecting the multiplexer back up again. So even though this functional block diagram is quite confusing to look at, the only part that we're going to be focusing on is just this top section up along here. So this chip works as a multiplexer and a demultiplexer. So this is why we have common out-in signals. So as well as being able to take 2 inputs to 1 output, we can also take 1 input to 2 outputs, just depending on which way we have the signals routed. But in our case, we just want 2 inputs to go to 1 output. So as you can see, if we just look along at this part along here, we can see that we have 2 inputs, AX and AY. Both of these inputs are then controlled by the A select signal over here. And then over here we can see we've got the output. Now it's also quite convenient because they've labelled which pins are which. So now I can work out how the hell I can actually rewire this back up again. So as we can see, we already have the final output LED connected to pin 14. So now we just have to connect each of these other signals up to their respective places on the chip. Alright, so I'll take the free running oscillator. We want that to come over into, let's just say pin 12. So if that's 14, 13, 12. And then we want the manual clock pulse to come over into 13. And then we take the select signal into pin 11. What was that? 14, 13, 12, 11. Hey, there we go. So now we can see that the final output on the multiplexer is following whatever is happening with the free running oscillator. Now hopefully if I flick the select signal to the other way, we should now be able to see the manual clock pulses coming to the final output. Hey, there we go. So now that we have our final clock output on the multiplexer, I can probably remove these extra LEDs that I've just put in. So in addition to the clock signal, I also said that I wanted to make the not clock signal. So for that, I just have a little 4049 hex inverter chip down here, which is pretty fresh, so I'm gonna have to bend those pins in a bit. Let's try and get this in here. So what I have here is just the pinout for the 4049 hex inverter, just so I can remember how the hell to actually wire it up again. I want that one to come to ground, and pin number 1 has to come over into the positive power rail. Sped this up a bit to make sure it doesn't die on me for whatever reason. So what I want to do is take the output of the clock into the input of one of the inverters. So I'll just use this first one up here. So just need to come over into pin 3, and then we should be able to see the not clock on the output. There we go. So now we can see that these LEDs are now doing the opposite from each other. And it'll also be the same with the manual clock pulse. We can see that when the button is not pressed down, we have no output on the clock. But because it's being inverted, we then have an output on the not clock. But then when I press the button, we now have a signal on the clock, which is then being inverted so we get the not clock. And this will just forever keep doing the opposite from one another. Now what we also have on the 4053 is our inhibit line. So if I quickly replace this wire, if I connect the inhibit line to the positive power rail, we should now see that we have nothing on the output whatsoever. Very nice. Then if I change it to the negative power rail, it'll go back to doing what it's meant to be doing. So we can see that by using this 4053 multiplexer chip, we're able to replace nearly all of the functions that we have with the Benita schematic. So rather than using an extra 3 chips, we can just use the 1 chip, which is perfect for what I want when it comes time to making the PCB. Now as I mentioned, the 4053 also has an extra 2 multiplexers. So when I first played around with this little chip, my thought was, well, why not make an extra 2 clock circuits? So I can create some different craziness and then have 3 different clock sources that I can play around with. And as I said, then those 3 clock sources, or the not clock sources, can then also go to a logic module where they can create a rhythm or repeating pattern out of the 3 individual clock sources. So you can imagine that all sorts of craziness is going to come in when I can use the clock, or the not clock, or the manual clock pulse. I could have one clock running really fast, I could have another one running really slow, and then the third one using the manual clock pulses. Now for this whole video, I'd love to be able to show you the process of turning this module into a final PCB. But the thing is, I already designed that PCB a couple of months ago. So let's just jump straight into KiCad and have a look at the PCB that I've designed. So we can see looking at the schematic that it seems pretty full on at first appearance, but it's actually relatively simple. On the left hand side here, we can see the 3 copies of each 555 timer circuit in their respective modes. A few things to note. The free-running oscillators and the manual clock pulse circuits are made up of a 556 timer, which is just two 555 timers in the same 14-pin IC package, just to save myself a bit of room on the PCB. The free-running oscillators also have two different timing caps to choose from, a 1 UF or a 0.1 UF, so we effectively have fast and super fast modes, adding to the craziness of the whole module. You can also see these labels on the outputs of each 555 timer circuit: X0, X1, clock select A, clock select B. These are just a market connection over into the 4053 multiplexer chip. We can see on the chip that we are utilizing the three 2-to-1 multiplexers, and then using each clock select signal circuit to control each of the multiplexers. We also have a switch connected to either 12 volt or ground on the inhibit line, so we can choose to turn the multiplexer on or off, for whatever reason I may actually need to do that. We can also see on the outputs of each multiplexer that we have a number of connections coming off them. We first have the indication LEDs for each clock signal, and then the output jacks. We then also make a connection over into each of the respective inverters to create the not clock signals, also with their indication LEDs and output jacks. Also note that with the jacks, we have these little X's to mark a no connection. This is because all the jack's ground pins will be wired behind the panel to each other and then to virtual ground. Which brings me to up the top, where we just have the Euro rack style header for power, with a few bypass caps and the resistor divider to create the virtual ground point. We can also see that each of the spare inverter's inputs have been tied to ground, just to prevent any noise inside the chip. Moving on to the PCB design, we can see that it's pretty small and compact, with so many components and traces. But this was like 2 weeks worth of playing around with the layout to get it right, so I really don't want to mess with it anymore. Plus, the smaller I can keep it, the less expensive the final cost will be, which is important in real-world engineering. Also hence my hesitation to use so many chips for the multiplexers. It would have been a stupid amount of real estate being taken up by so many chips for such a simple function. We can also see my little shout out or credit to Ben for the design, and then myself for modifying it. But I've also made these fun little clock pictures, just to test the limitations of the silkscreen machine at the PCB factory. But I have a feeling that all these little symbols will just be a blob. But hey, whatever. And taking a quick look at the 3D viewer, we can see it'll be a pretty nice looking little number. Maybe a little cluttered, but it's my second ever design, so I'll take it for how it is. Also note all these header pins for the switches and pots. These are just representative of the wired connections that will be made to each component on the panel. They won't actually be a part of the final design, but it's just my way of getting a small enough pad with the connections where I need them. Well, the only thing left to do is just place the order now. Alright, let's order this bad boy. So there's not really much more I can do until it arrives now. Join me next time in part 2, where we'll start and make the PCB, make the panel, and put it all together and test it out. And if you've enjoyed this video, don't forget to like and subscribe and all that good stuff. Until then, see you next time. It's got to be here in a minute now. Come on.